All right, let's talk about one of the most basic, but also one of the most important choices you have to make as a developer: arrays versus linked lists. Now, it might sound simple, but getting this choice right or wrong can seriously impact how well your app performs. So let's dive in. You've been there, right? Your application is just humming along, everything's smooth, but then you do one tiny thing, like add a new item to a list, and the whole thing just freezes. It takes forever. So what is actually going on under the hood? This is the exact problem we're going to solve today. So let's kick things off with an old friend, the array. We all know them. We probably all use them by default. I mean, they're simple, they're predictable, but that simplicity, it's hiding a pretty big performance trap. The most important word on this slide is contiguous. All that means is that every single item in an array has to live right next to its neighbors, side by side, in one big, unbroken chunk of your computer's memory. Now, this is awesome for getting to an item fast. If you know its index, you can just jump straight there. That's what we call a one, or constant time. But that same feature, well, it's also its greatest weakness. Okay, so what happens when you need to stick a new element right into the middle of an array that's already full? You can't just put it there. You literally have to make room. That means taking every single element after that spot and shifting it one position down the line, one by one. This is an ON operation, which is just a fancy way of saying the time it takes gets longer and longer the bigger your array is. This is why your app grinds to a halt. So, how in the world do we get around this shuffling nightmare? Well, we can turn to a much more flexible data structure, the singly linked list. A linked list is totally different. Instead of one big block of memory, it's more like a chain of individual nodes. Each little node holds your data plus a pointer, which is just the address of the next node in the chain. They don't have to be neighbors. They can be scattered all over your computer's memory, giving them some serious flexibility. And look how elegant this is. To insert a new node, we don't have to move a single piece of data. We just do a little bit of pointer magic. We tell our new node to point to the next one in the chain, and then we tell the node before it to point to our new one. That's it. It's a constant time O of 1 operation, and it doesn't matter if the list has 10 items or 10 million. So problem solved, right? Well, not quite. Turns out every hero has an Achilles heel, and for our singly linked list, it's deletion. We fixed the insertion problem, but in doing so, we've created a brand new one. This quote from a contributor on Stack Overflow just nails the problem. To remove a node, you have to patch up the chain, right? You need to tell the node before the one you're deleting to skip over it and point to the one after it. But here's the kicker. In a singly linked list, it's a one-way street. You can only move forward. You have no idea which node came before. So to delete a node, you have no choice but to start all the way back at the beginning of the list and walk through it one by one just to find that predecessor. This is an O of N operation, which is just as slow as the array insertion we were trying to get away from. We're back to square one. So how do we get the best of both worlds? How do we get fast insertion and fast deletion? Well, we need an upgrade. Enter the doubly linked list. The solution is actually pretty simple. We just add a second pointer to every node, a previous pointer. Think of it like a train. A singly linked list is like walking from the engine to the caboose. You can only go one way. A doubly linked list is like a real train. You can walk between the cars in either direction. And here is the big payoff. Because every single node now knows who came before it, deletion becomes an O of 1, constant time operation. You have the node you want to delete, you just look at its prev and next pointers, and you link them directly to each other, completely bypassing the node you're removing. No searching needed. It's incredibly fast. Okay, this is all great in theory, but where do you actually use something like this? Let's look at a super common data structure, the queue. A queue is exactly what it sounds like. It's a line. The first person to get in line is the first person to be served. In the programming world, we call this first in, first out, or FIFO for short. You add items to the back, that's called enqueuing, and you remove them from the front, that's dequeuing. And trust me, queues are absolutely everywhere in technology. They manage the jobs you send to your printer, they handle all the incoming requests on a busy web server, and they even help schedule all the different tasks running inside your computer's operating system right now. So this brings it all together. The perfect way to build a high-performance queue is with a doubly linked list. Why? Because enqueuing is just adding to the end of the list, and dequeuing is just removing from the front. With a doubly linked list, both of those operations are O of 1. They're instant. It is a perfect structural match. All right, let's zoom out and put this all together. Really understanding these trade-offs is not just academic. It's essential knowledge, especially if you find yourself in a technical interview or you're trying to design a really high-performance system. Think of this table as your ultimate cheat sheet. If you need to grab elements by their index super fast, the array is your winner, hands down. If you need really fast insertions and don't care much about deletion, a singly linked list is a great choice. But if you need both fast insertion and fast deletion, especially in the middle of a collection, the doubly linked list is the undisputed champion. You see, there's no single best data structure. There's only the right tool for the job you're trying to do. So the next time you sit down to build something, just take a second to think. What are you going to be doing most often? Accessing, inserting, deleting? Answering that question will point you to the most efficient choice, and it will help you build faster, smarter, and better applications. Thanks for joining me.